Assalamualaikum and hi everyone. We will be presenting on nuclear magnetic resonance spectroscopy, NMR spectroscopy. So before I proceed with the presentation, I would like to introduce my group members. First, Goh Ziwei, he will conduct our Q&A session. Then, Siti Nozaira binti Ramli, she will be presenting on the example of NMR. And Alia Natasha binti Anwar Musadat will explain to you on how does NMR work. So lastly, myself, I'm Nur Azilma binti Nur Azlan, will explain the introduction of NMR. I believe you guys are familiar with this spectroscopy since we have learned this before. So let's proceed. Other than IR spectroscopy, X-ray spectroscopy, NMR is also one of the spectroscopic methods that can be used to characterize the polymers. It is a spectroscopic technique which is used to observe local magnetic fields around atomic nuclei. The basic principle of NMR is the nucleus of an atom placed in a magnetic field and exposed to electromagnetic radiation to resonate at a specific frequency of that radiation. In other words, many nuclei have spin and all nuclei are electrically charged. But if an external magnetic field is applied, an energy transfer is possible between the ground state energy to a higher energy level. NMR also can be used to identify monomers and polymers, and also elucidation of constitutional, configuration, and conformational structures of polymers and copolymers. The determination of various polymer structures includes polymer tacticity, polymer molecular weight and molecular weight distributions, copolymer composition, monomer reactivity ratios, monomer sequence distribution in the copolymer chains. NMR spectroscopy can determine the proton environment in the molecule. Besides, the different local chemical environments surround any particular nuclei causes them to resonate at slightly different frequencies. This is what happens when a nucleus being more or less shielded than another. This is what we call the chemical shift. The proton NMR chemical shift is affected by nearness to electronegative atoms and unsaturated group. Equivalent hydrogen have the same chemical shifts. Each proton in the molecule has its chemical shift and is expressed in ppm by frequency. So the reason why it is expressed in ppm by frequency is because hydrogen bonding also changes the electron density in proton NMR, causing a larger shift. These frequency shifts are small than the fundamental NMR frequency difference on a scale of Hz as compared to megahertz. The chemical shifts of proton nuclei in various chemical environments have been determined by measuring the proton spectra of a large number of compounds with non-relatively simple structures. So, Alia Natasha will explain more on how NMR spectroscopy works. With that, thank you.
In this part, we will discuss on how NMR works. As we know, the essential part of NMR spectrometer is magnet. So if we have sample, the samples will insert in the center of the magnet. And inside, there are two coils of wire that are used to excite the sample and record signal response at radio frequency. The tube that contains the sample will spin around its axis to ensure that all parts of the sample experience exactly the same magnetic field. One of the coils surrounding the sample tube generates the electromagnetic radiation at constant frequency. As the field strength grows, the energy level of the magnetized nuclei in the sample split further and further apart, and at certain point, the splitting will exactly match the energy of the radiation emitted by the generator. and this will make the nuclear spins in the sample excite to the higher energy level and resonance will occur. Soon, it may return to lower energy level and re-emit the radiation which is recorded by the second coil as a tiny current, and the current then is then amplified and processed to give NMR spectrum. In this part, we will learn on how to interpret the NMR signal. So there are three things we need to take into account for any resonance on spectrum. First is the chemical shift, second is the integration, and third is the splitting. Chemical shift tells us about location. Where is it on the spectrum? Is it on upfield or downfield? Chemical shift tells us about the chemical environment of a particular proton. The closer that proton is to some electronegative element, the electronegative atom is going to have a de-shielding effect because of its electronegativity withdraw the electron density of the proton away from the nucleus. This is called a de-shielding effect, and this will cause signal to be more downfield. More downfield means closer to the electronegative atom, whereas upfield means farther away from the electronegative elements. So, in conclusion, higher electronegativity, higher the de-shielding effect, and reduce the electron density, thus the chemical shift will be increased. Integration tells how many chemically equivalent protons are generating that peak, and splitting tells us about chemically equivalent protons will generate the same resonance, but that resonance will be split into a certain number of smaller peaks depending on the neighboring protons. So this is the example of molecule ethyl acetate for us to better understand about how to interpret the NMR signal. So in this spectrum, we have three different resonance to expect. Let's call these A, B, and C. Looking at A first, for the chemical shift, A is near to a electronegative atom, so we expect it to be relatively downfield, which is far from the reference peak. Then, it is integrated to 3 because there are 3 protons. There are no neighboring hydrogen, so it will not be split at all. So we are expecting a singlet peak here, and on the graph, the spectrum for A is at 2 ppm. For B, 2 hydrogen is adjacent to the oxygen atom, which is very electronegative. So we expect it to be downfield because downfield is the atom that are near to the electronegative atom. There are 2 protons, so it is integrate to 2. And there are 3 neighboring hydrogen, so it will be split into quartet because n plus 1, which is 3 plus 1 is 4, so it will be split into quartet. So the signal for B will be at 4 ppm. And lastly for C, it is not near to any electron withdrawing, so we expect it to be upfield. There are 3 protons, so it is integrated to 3. There are 2 neighboring hydrogen, so it will be split into triplet because 2 plus 1 will be 3. Hence, the signal for C is around 1.3 ppm.
So the last one would be examples of application in NMR spectroscopy. So I included 4 examples of application. So let's begin with the first one. The first one is cancer research. NMR spectroscopy is valuable in cancer research, which NMR can observe choline, phosphocholine, and glycerophosphocholine in both prosium and 31-phosphorus NMR spectra of biological fluid samples from cancer patients. Other than that, it is used in the development of smart delivery system for drugs, which NMR can identify acetaminophen, ibuprofen, aspirin, valproate, carbamazepine, and pseudoephedrine as parent compounds or metabolites. The next one is agriculture. Agriculture helps us understand the molecular basis of photosynthesis and other processes, thus making it possible for us to know which crop strains are best suited for different environment. Can also identify molecular evaluation of sample in semi-solid state, such as plant tissues and soil components. The third examples is invention of batteries. NMR plays a crucial role to establish the molecular details of the battery's energy storing function. The last one is foodomic. NMR spectroscopy can be used in foodomic because of its quantification and identification, short time and low cost needed for analysis, and also high number of metabolites that can be measured through a single pass. And it is also because of higher sensitivity of NMR focus on hydrogen, which is why NMR is preferred for foodomic studies.